So in this section, we're talking more about the definite integral, and we're introducing a notation that we've actually already seen back when we were doing trapezoidal and Simpson's rules, namely that the exact area is denoted by this thing called the definite integral. So it looks an awful lot like the antiderivative, but it is not the antiderivative because it has these numbers on the bottom and the top. Okay, it is definitely related to the antiderivative, but this time instead of getting a function as our answer, we're getting a numerical value. That numerical value represents the area under the curve f of x from x equals a to x equals b. So this is exactly what we've been approximating for the past week or two. So with this familiar region that we talked about in the intro, we found a lot of different approximations for the area of region R. The exact area of region R can be represented by the definite integral from x equals 0 to 2 of the function, which is 5 minus x squared, and always have that dx. Okay, that dx is going to be analogous to your delta x, which is the width of each of those rectangles. The 5 minus x squared, that's going to be your height of each rectangle. So this is going to be the area of each rectangle, and we're going to take the sum from 0 to 2. So this antiderivative symbol is actually a funny looking S, and that's actually where it comes from. So anyway, we can actually evaluate some definite integrals without the use of calculus. For example, the definite integral from 2 to 5 of the function 4 with respect to x. Well, let's see, 4 is a horizontal line, right? When we graph a constant, we get that horizontal line at y equals 4. This is y equals 4. And our x values go from 2 to 5. So we're asking for the area under the curve between 2 and 5. Well, that happens to be a rectangle whose dimensions are 3 by 4. So this is just equal to 4 times 3, or 12. So obviously, normally we're not going to be finding a definite integral of constants because that's an answer we could have found using tools we learned in geometry, but it's sometimes useful to remember how constants work with definite integrals. On this next one, we've got a linear function, 2x plus 1. So a slope of 2 starting at a y-intercept of 1. We've got ourselves this line right here going from x equals 0 to x equals 3. And again, we don't need calculus to find the area of this region because all the edges are straight. So we could think about this region as a trapezoid, or we can think about it as a rectangle and a triangle, whichever way you prefer. I'm going to use the, I guess since I've already divided it up, I'll use the rectangle and the triangle. So we've got 1 and we've got 3. For the area of the rectangle is 1 times 3 plus, we've got this triangle whose base is 3 and whose height is 1, 2, 3, 4, 5, 6. So 1/2 base times height. So that's going to be 12. Oh, okay, another 12. And then we get to this one right here where we're like, well, this is not a line. I'm not sure what this graph looks like, but I think that we do know what this graph looks like. If we think about y equals the square root of 4 minus x squared, this should look familiar to everyone. And if it doesn't, then square both sides and add x squared to both sides. And suddenly we see that this is just the equation of a circle whose center is at the origin and whose radius is 2. So if we have a function, then we don't have a circle, right? So since we have the positive version of this, we just have the top half of the circle. And we're evaluating the region, the area of the region from -2 to +2. So that's just 1/2 the area of the circle. So this is going to be 1/2 pi r squared, which is going to be 2 pi. So sometimes we're able to use geometry to evaluate these definite integrals, and we don't actually have to use methods of calculus. So that's what this section is kind of all about. Then we start playing around with some things, like what if f of x is not non-negative? In other words, it could be 0, it could be negative. So, for example, if I look at the graph of negative x, that goes down here, right? It's a slope of -1, and we go from 0 to 2 in this case. We're asking for the area, quote, under the curve. Well, under the curve goes on forever. So it's kind of a misnomer. We're not really doing under the curve. We're finding the area between the function and the x-axis. Okay. Remember that our rectangles that we were drawing before always were based on the x-axis. So if we draw these rectangles right here to try to approximate this, well, then we see that our heights are negative, right? The height of this rectangle might be -3/4. The height of this rectangle might be -1.5. I don't know, I'm just guessing. But they're definitely negative because we're going down. So as x gets bigger, our delta x values are positive. But our heights, our y values, are negative. So basically, if we find the area under the x-axis, we're going to call that a negative area. Or rather, the definite integral is going to give us a negative answer. So any area that we find underneath the x-axis is going to be considered negative. So this is still a triangle, 1/2 base times height. So 1/2, the base is 2. And the height, I'm not going to call this 2, I'm going to call it -2 because we're going down, which is something we never really did in geometry, right? We just said, well, area is positive. And area is still positive, but we're still denoting that the negative indicates that we're finding this area underneath the x-axis. So that works out to be -2. Sometimes we see something like this where we've got a y-intercept of 1, so we're starting here. And actually, we're going to have an x-intercept of 1 as well. So when we graph that line 1 minus x, we're going to go like this until we get to x equals 4. So sometimes when we look at our rectangles, we're looking at rectangles that have a positive height. And sometimes we have rectangles that have a negative height. So basically, we have to keep track of each one of these separately and find each area, and anything that's above the x-axis will add, and anything that's below the x-axis will subtract. So here is a triangle whose base and height are both 1, so that's 1/2 base times height. And here is a rectangle whose base and height are both 3, but this is a -3 because we're going down, so I'll do minus 1/2 3 times 3. Okay? And that's a positive area for the first one because it's above the x-axis, and a negative area for the second one because it's below the x-axis. So we have 1/2 minus 9/2, or -8/2, which is -4. Okay? And then finally, we've got this interesting one here where we've got the sine of x. Okay? Well, we don't really have a circle like we had on that other curvy graph. We have a sinusoidal graph. Right? So we go from 0 to 2 pi. But something you should notice about this is it's periodic. That's the number one thing to know about any trig function, is it's periodic. And if we look at this one full period, we've got this hill and we've got this valley. And since they're symmetric, we've got a positive version and a negative version of the same thing. So we end up canceling each other out, and that integral equals 0. Now, what happens if we take a look at these two guys? You'll notice that the integral goes from a to b of f of x versus the integral goes from b to a of f of x. Well, this way, if we're going from a to b, delta x is positive. And if we go from b to a, then delta x has to be negative because we're going smaller. So if we flip the order of the integrals, then we're going to flip the sign of the answer. So just like we could have a negative height, we could have a negative width as well. So just flipping the order of the bounds of integration is going to flip the sign of the answer. So that's useful information sometimes. So if we try to find the area here, well, we're going to start with a graph, -4, 1, 2, 3, 4. And we'll go up 2, so here to here to here. 1, 2 to here. Well, I'm getting tired of this. So 10 minus 4 is 6. So this is the point 5, 6. 6, and we're going from x equals 2, which is the x-intercept. So it looks like we're just finding the area of this triangle. But keep in mind that we're starting with 5, and we're going to 2, so that means that delta x or dx is negative. So we'll find the area of this, this triangle, but this time the x value of 3 is actually a negative 3. The height is 6, so the answer works out to be negative 9. Okay, so if this were the integral from 2 to 5, then we would have a positive 9, but since we flipped the order of the integral, then it'll be a negative 9. Back to the circles, the semicircle business over here. This is the same semicircle, but it's been shifted down to, right? So it used to be like this, but now we're going to shift it down so that it goes down to here. That's what that minus 2 does to a graph. Okay, so in this case, we're going from 2 to negative 2. So dx is negative. We're also looking at heights that are below the x-axis. So the y value is also negative. Interesting. And then how do we find the area of this crazy region right here? Well, you might recall problems like this in geometry where we said, well, I know how to find the area of what's not what I'm interested in, so maybe I'll subtract that, right? So we've got this rectangle whose dimensions are 2 by 4, so that's going to be 8, but we want to subtract out that semicircle, which we already calculated to be 2 pi, and that will be your final answer. That's a positive value because this is approximately 6. 8 minus 6 is positive. We expect a positive answer because we've got a double negative situation going on here, right? We've got x is going from 2 to negative 2, so dx is negative, but also our y values are negative as well because we're below the x-axis. A few other properties to throw out there. If we start at A and end at A, we're not going anywhere, so our complete width is 0, so our area is going to be 0. If we start at A and stop by at C and then take a detour and then go from C over to B, well, that's the same as going directly from A to B. Okay. If we have a scalar factor, well, we can just factor that out. We were pretty used to seeing that. As long as k is a constant, we're allowed to do that. And then just like with limits and just like with derivatives and just like with antiderivatives, we can go term by term. So the integral of the sum or difference is the same as the integral as the sum or difference of the two integrals. Whether that's a plus or a minus, we're allowed to separate this out into two separate problems. So real quick at the end here, from 2 to 2, that's got to be 0. This is going to be from 1 to 2 and from 2 to 3, so that's going to be from 1 to 3 of 6 x squared dx. When we're told that the integral from 1 to 3 of x squared dx is 26 over 3, so this is 6 times 26 over 3, which is 53. No, what am I doing? This is 60. I can't double. It's 52. 52. All right, and then here we have basically this is going to be 26 thirds plus 1/4 of 20, right? So that's going to be 5. 26 thirds plus 5. 5 is 15 thirds. So this is going to be 41 thirds. And then lastly, from 1 to 5 and 5 to 3, well, that's the same thing as 1 to 3, right? So we're going to factor out that 2, go from 1 to 3. That's a cubed. So that's going to be 2 times 20, which is 4.